Hello, hello, and welcome to a video on currency control theory. This will start us out on this sort of last module of our course, where after having kind of gone into the details of a database management system, how things are stored, how memory is managed, what algorithms we would use, how query operators are functioning, and how we optimize them. Now we're saying, all right, from the high level of this database management system, where it's coordinating all the different stuff going on, how is that actually functioning? And so here's some sort of motivating reasons why we want to talk about this. What if we have two simultaneous updates to the same tuple? Right? This is something that can easily happen if we have kind of multiple users interacting with the database, and they both try and update the exact same piece of data at the exact same time, and we need to be able to avoid lost updates. So we need the database to provide some way to resolve this situation in a consistent and predictable manner. And this is where concurrency control comes in, and that will be the topic for this video as well as the next two. So this is the next three videos will be all about how we deal with concurrency at sort of this logical level about the database, rather than the kind of concurrency we focused on up till now, which is kind of within the internals of the database, whether it's within a query or within an index like a B+ tree. How do we allow multiple threads to interact with those structures or to perform work in parallel? Here we have the same sort of questions, but at this logical level, higher level of the database. Another motivation is what if we have a power failure in the middle of some purchase? So I go to some online store, I attempt to purchase a t-shirt, and the database is my bank's database has transferred money out of my bank account, but not yet transferred it in to the account of the t-shirt store, and then there's a power failure. And so what should happen? How does the database recover from the fact that it was in the middle of this task when kind of everything fell apart? And so this is the issue of durability. We want our database to be robust to these sorts of failures, and in particular we want it to be able to recover. We want it to have recovery mechanisms so that if such a failure occurs, not all is lost. And this will be the next two videos after our three on concurrency control will be on this recovery idea. And both of these topics kind of permeate throughout the different parts of the database that we've talked about. So that's where we're coming to them last, now that we've assembled a lot of the pieces. And a fundamental concept that we're going to use to serve kind of both of these things is the idea of a transaction. And so a transaction is just going to be the execution just an execution of a sequence of operations on some shared database. And so this, an example, would be a SQL query. Could be the source of one or part or all of this sequence of operations. And this is going to be the it's going to be the basic unit of change in the database, meaning that partial transactions are not going to be allowed. So if there's some sequence of operations that are part of a single transaction, they are going to be atomic. They're all going to happen or none of them are going to happen. And in fact, atomic is a term that will come up throughout our discussion of concurrency control, because it's one of the properties that we want a database system to guarantee when it comes to transactions. So an example of this sort of sequence of operations, again, I want to buy a T-shirt, and so we want let's say I want to buy a $15 T-shirt, and so we might need to first check if I have $15. Check my bank account. Do I have the money? Then deduct $15 from my account and add those $15 to the retailer's account, the person who's selling the T-shirt. And what we don't want is for part of these steps, particularly I don't want part of these steps to execute, to happen, to lose my $15, but never having paid the retailer, I'm not going to get my T-shirt, I'm going to be out 15 bucks, I'm going to be very sad. So I want all of these things to happen or none of them to happen. And so one way that we might support transactions, would be kind of nice and simple, is what if we had a system that just said, do one transaction at a time, and on the board I'm going to be typically abbreviating transaction TXN. This is something you'll commonly see. I'll do it to save a little time writing. So if we just do one transaction at a time, that means many transactions can be arriving, many people trying to buy T-shirts, and our database is just going to take one at a time, do its operations, and so we're never going to have an issue where like two transactions are trying to do things simultaneously, both trying to say add $15 to the retailer, and and potentially getting in a situation where one would overwrite the other. If we're just doing one at a time, and in particular, if we're just doing one at a time, and we start out by making a copy of the whole database, and then we only make changes to that copy, and so we would change the copy, and then if we get through the whole transaction, it all succeeds, then we would just change a pointer to say, all right, the database file is actually this copy instead of the original that has the changes. And so this would give us these atomic transactions, but would have some major drawbacks. We don't want to copy the whole database each transaction. That would be very costly and slow if we have a large database. And we also would like to be able to run more than one transaction at a time. And so what our goals are here we want simultaneous transactions because this is going to give us better throughput, more transactions per second. And the more transactions we can do per second, the more people can be buying t-shirts from our store, and that's very good. And we also can get faster response time. So each individual transaction will, on average, complete faster if they don't have to all wait in line and they can actually run at the same time. But even as we have simultaneous transactions, we want correctness and fairness, meaning that that all of our fairness meaning kind of all transactions get a chance to run. We're not going to have, if we get rid of our single file line for transactions, we still want it to be the case that all transactions will get a chance to run, and we don't have one kind of sitting there forever as a bunch of others jump ahead of it when we're doing simultaneous ones. And we want things to be correct. We don't want having simultaneous transactions running at the same time to interfere and to lead to incorrect results for our queries, for our transactions. So we're going to kind of represent our database as some set of named objects. And these objects could be attributes, tuples, pages, tables, or even whole databases. The sort of techniques that I'm going to talk about are agnostic to specifically what these objects are, just that a database, as we've talked about, has all sorts of different objects in them that we might want to coordinate access to. So when we're talking about a technique applied to these named objects, we're just assuming these are all objects of the same type, but they could be these different things. And a transaction will perform reads and writes on these database objects, and so we'll represent those doing something like we can read object A, a transaction will write object B, and so this is the notation that I'll use for describing what a transaction does as sort of as the database views its operations, because an important fact is going to be the database is not going to know the details, the objective of the operations in a transaction. Is just going to see reads and writes to specific objects, and it will need to use that information to coordinate. So when a transaction starts, so transactions start with a begin statement. So this is in SQL. You can write begin, and that indicates you're starting a transaction, and all operations that follow begin will be part of that transaction. And then transactions will end with commit, which means, all right, this is the end of the transaction. Kind of make these operations a sort of permanent part of the state of the database. Or they end with abort, which says, all right, this transaction, it's not actually happening. Make it as if none of these things happened. And this a transaction may abort either because the database forces it to. The database says, all right, this transaction is invalid for some reason, it needs to abort, or the transaction itself may, after some amount of time, abort. And this would be, there are different scenarios where I initiate this purchase to buy a t-shirt, but then at some confirmation step I say no, actually I've changed my mind, and so a transaction may have started in the database but then is aborted. And so when this abort happens, all the changes that have resulted from the current transaction must be undone, because our transactions have to either happen in their entirety or not happen at all. And so now we kind of get to the heart of what databases are going to provide. So correct transactions are said to be ACID. And this is an acronym standing for Atomicity, meaning that this is our all or nothing. They need to be consistent. So we have consistency, and this is this means that the database kind of looks correct after the end of a transaction. And stated more formally, it means that if a transaction is consistent and if the database is consistent, then at the beginning of the transaction, then the database is guaranteed to be consistent at the end of the transaction. And so I'm using sort of vague words here that it looks correct, it's consistent, and this consistency property tends to be a little bit hand-wavy in terms of what exactly it means. In one sense, a database is consistent if it kind of accurately reflects the real-world thing that it's modeling. So for example, if you have a database of people, you might say the age cannot be less than 0, right? People can't have a negative age. And so if the database is consistent, there are no negative ages, and the transaction is consistent, it doesn't make any of the ages negative, then at the end of the transaction, the database will still be consistent. This consistency can also mean that a transaction will be able to observe the committed changes of previous transactions. But I've heard that perhaps consistency was kind of added to these properties primarily to get this nice acronym ACID, and it's kind of one that we'll focus less on than these others. So the I is as if alone, so it means that the transaction should have the illusion that it is the only transaction that is occurring. It should be isolated from other concurrent transactions. And then finally, we have durability, which is our survives failures. That if a transaction commits, then those changes that it made should persist within the database and not be lost. And so when a database is ACID compliant, or it supports transactions, that means that its transactions have these properties, have these guarantees in terms of their behavior. And one note is that when we think about NoSQL systems, so kind of not relational databases, particularly as they kind of became more popular or more initially created, they tended not to support transactions. They tended to sacrifice atomicity and isolation because it made the implementation simpler, it made performance better, but these guarantees were not present. You could have partial transactions. You might have transactions that interfered with each other. And so it's a trade-off in terms of how strong, how robust do you want these guarantees to be versus kind of complexity of implementation and performance, because it does take some additional work to ensure these properties. So let's go through each of these kind of one by one. So we'll start off with our atomicity. So we have two scenarios that we want to make sure that our database is correct when it comes to atomicity. So kind of our scenario number one would be, let's say that we deduct $15 from my account, but then later on the transaction aborts. So we've deducted this $15, but then the transaction aborts, and scenario two would be we again have deducted $15 from my account, but then we have that power failure potential that I brought up earlier. So in both of these cases, we want to ensure this atomicity problem, that that each of these transactions needs to, either all of it needs to happen or none of it, which means that in both of these, we need to somehow undo this minus $15 because the transaction did not complete, did not commit, which means its effects should not be present in our database. So there's kind of two categories of approaches to this. So our solutions, our first solution would be logging. So this does not mean the sort of log print statements that you might use for debugging. It means we're going to write down the operations that the transaction is doing as we do them. We're going to keep a log of what the transaction has done, and we're going to do so in memory and on disk. And this means that if we've written down the operations as we do them, in scenario 1, we wrote down the operations. They're in memory, a record of a log of what we've done. We abort the transaction, and then we can just go through our log and undo all the operations that we wrote down as having performed, and so we can put the $15 back in my account. In scenario 2, as we do these operations, we've also written them to disk. And so when the power fails and when the system eventually comes back online, it can look at the log on disk to sort of figure out what was happening at the time of the failure. Is there anything that needs to be rolled back, that needs to be undone? And it can find the record there. Now, if we were in the middle of some transaction and the changes of that transaction exist only in memory and had not been written out to disk, and we have this power failure, well, we lose those changes and potentially lose the record of them we have in memory as well. But that's okay, because what's on disk is the original unchanged data, and when we start the database back up, that's the data we have, and it's as if that transaction never happened, if it only ever was present in memory and was never written out to disk. So logging is what basically every database management system will do, is we'll take this logging approach. It's useful for more than just Atomicity. It's useful for auditing as well as efficiency. So banks, for example, want to keep a record of all the sort of transactions that they've done. There are in the US, federal regulations about kind of the duration of time for which a bank has to keep records. And so if your database system keeps this log of every operation, that's something that you can go and audit, you can look through to determine what's happened. Or if something goes wrong with some application, you can go to the log for the database, try and use that to help you figure out what's going on. The efficiency part is, say we're making a bunch of updates to data that's in memory. And if we wrote out each update as we made it, that would be a bunch of random I/O. They're updating stuff all over the place. If instead we keep a log of these updates, we can then collect a number of updates that we need to write out to disk together, and then organize them so that we are doing the writes in sequential order. So there are updates to different different tuples, so they're not affecting each other, and we can reorder them such that we do the writes in sequential order and get better performance. So logs can be useful for efficiency as well. The second possible solution to atomicity has a pretty cool name, shadow paging, and this is a form of that kind of making a copy of the database that was sort of my straw man example at the beginning. But in this case, we're doing something kind of a little more targeted, where we're making changes only to copies of, we're just copying, say, the page or pages that we're making changes to, and then replacing the original pages when the transaction commits. And so this is actually what System R, IBM's original relational database, did. It used shadow paging, and this can avoid needing to keep a log, particularly if the database is single-threaded. But again, logs are useful for other reasons as well, so you're almost always going to keep one anyway. This makes recovery very simple. If we just have a copy of the page and we want to abort, we just throw away the copy. We have the original stored somewhere else. But these copying of pages and so on, that's just kind of unavoidably slower than logging. So this shadow paging is there are just like a handful of systems that do this. It's quite rare. All right, so we're using logging to sort of undo things when necessary to give us our atomicity. So let's move on to our consistency. So there are kind of two types of consistency that we're going to care about. So we are going to care about database consistency and transaction consistency. And our database consistency is things like, as I was saying, our data represents the real world, so ages can be negative, and we have some constraint within the database that checks and enforces this, and that future transactions see the changes from past committed transactions. So this is, if we just have our database stored in a single place, a single file, this is pretty trivial, that when we make changes to that file, future transactions are going to see it. But if we have a distributed database, we have the files stored in different disks, different computers, maybe computers very far away from each other. You have Google's data in data centers all over the world, for example. Then this requirement that future transactions see the changes from past transactions becomes a lot more challenging to actually enforce. And some systems don't provide kind of a strong guarantee like this. NoSQL systems often provide what's called eventual consistency, and that means that eventually the changes from a transaction will sort of be reflected across the distributed parts of the database. And so this is something that's mainly relevant in that distributed context. Transaction consistency is if the database is consistent at the start of a transaction, then it should be consistent at the end of the transaction. This is actually going to be the application's responsibility, whatever application is generating these transactions, it's going to be responsible for generating transactions that are consistent with what the data in the database is, and that the database isn't necessarily going to be able to enforce transaction consistency because it can always be given transactions that will kind of do strange things with the data and kind of make it inconsistent. So that's all I'll say about consistency for now, and I'll spend kind of the rest of our time in this video on isolation. How are we going to make our transactions run as if they're the only thing running, even though we're running kind of more than one at the same time? All right, so let's start out with an example. We have transaction 1, begin, A equals A minus 100, B equals B minus 100, and then commit. And so transaction 1 subtracts not B minus 100, but B plus 100. So transaction 1 transfers 100 from A to B. And transaction 2, begin, it will add 6% to each of A and B. So you can think about this we can think of transaction 1 as if it's transferring $100 between two accounts, and transaction 2 as adding 6% interest to each of the accounts. And so when our database goes to run these two transactions, they come in at the same time, and it's going to run them simultaneously. There are many possible interleavings of these operations that, as we've talked about when we've talked about concurrency before, we're looking at kind of the system could each of these transactions we're going to execute in order, but they may be interleaved in many different ways. And what must be true when we finish executing them is that our A plus B needs to equal (2,000 times 1.06), and that only makes sense if I've told you that A and B both start out as 1,000. So what I'm saying with this is that there's no guaranteed order between our two transactions. We don't know which one is going to happen first, but in order to provide this isolation property, we must in order to make these transactions, kind of give them the illusion that they are the only thing running, we have to end in a state that is consistent with some sequential ordering of our transactions. So the state of the database at the end needs to be as if we did T1 and then T2, or as if we did T2 and then T1. And so we don't have some guaranteed order between them. They come in at the same time. The database could execute one and then the other, or at the same time, and their different operations interleave. But we need the ending state to be consistent with some kind of sequential ordering of them in order to provide this isolation property. Because if we don't, if it's not consistent with either of these, then it's the case that the transactions did not kind of observe the world, did not affect the world as if they were the only thing running on the database. We could have kind of all of T1 happen and then all of T2, or the reverse. And in either case, we're going to have our A plus B as 2120. But there are kind of interleavings of these running simultaneously that are consistent with this picture. So we could begin T1, update A, then begin T2, update A, then switch back to T1, update B and commit, then T2 updates B, and commits. And when we execute this, we're going to subtract, A is going to be 900, then we'll add 6%, and so A will be 954. We'll add 100 to B and then do its 6%, so it will be 1166. And so this is like the world where we did all of T1 first and then all of T2, even though that's not what actually happened. We had their different parts interleave, but we can observe that T1 did things with A, and then T2 did. T1 did things with B, and then T2 did. So we could, so this is equivalent to a schedule, to a kind of ordering of our operations, as if we had done all of T1 and then all of T2. And we want to ensure that only these sorts of interleavings are allowed, because if, for example, we reorder these operations on B, so that T2 does its operation on B before T1, we end up in a situation where A is 954, but B is 1160, and so A plus B is 2114, and we're missing $6. Like, we started out with 1,000 and 1,000. We should have just done a transfer and applied our interest, so we should see 2120. We only see 2114, this is an example of kind of a bad interleaving, something that would violate our isolation principle. And so this is sort of what I've been referring to as the schedule. That if we kind of write down this order of operations for what simultaneous transactions will do, that's what we'll call a schedule. And if we kind of and I said at the beginning that our database is going to view this only in terms of reads and writes to particular objects. That it's not going to know kind of what the semantics of that this is like a computing interest, that this is doing a transfer, and so if we switch this over to kind of what the database's view of this are, in order to do A equals A minus 100, it's going to need to read A and then write A. It reads the current value of A, it subtracts 100, it then updates A with the new value. And similarly, all of our operations are going to be a read followed by a write, read B, write B, and then lastly we would have this do its read B, write B. And so we're converting these kind of these sort of statements into what the database will see, which is just accesses to particular database objects in terms of a read or a write. And so how do we know if a schedule is correct? I've gone through particular examples with, all right, we can have a good interleaving, we can have a bad interleaving where some data goes missing. But what it means, what we're going for is a correct schedule is going to be one that is equivalent to some sequentials, to some serial schedule. So our example of a good interleaving was good because it was equivalent. It had kind of the same effect as some serial schedule. So are the kind of formal properties, the kind of this concurrency control theory that we're building up. We're saying that a serial schedule is one in which there is no interleaving of transactions. Kind of each transaction happens as a whole chunk, and there's no back and forth. And when we say equivalent schedule, what we mean is that the schedules have the same observable effects. So that when we execute one schedule, what we can see at the end is the same as executing some other schedule. And so that's why in these examples I was looking, what do A and B end up at? Are they equivalent to some other schedule? And in the bad interleaving, it was not equivalent. So what we're going for is to make our schedule serializable. So our serializable schedule means equivalent to a serial schedule, which is in fact what I said a correct schedule was. So So if we can get a serializable schedule, some schedule that's equivalent to a serial schedule, then it will be correct in terms of this isolation property. And so we'll need a kind of a notion of what it means to how do we determine if a schedule is equivalent, other than like running multiple schedules and seeing what happens. That we're not going to kind of we're not going to have a bunch of kind of playground databases to try out different schedules on and see what happens. We're going to need some way to judge a schedule and tell, is this correct? And so to formalize this equivalence, I'm going to say that we're going to have a notion of conflicting operations. And a conflicting operations are from different transactions, and they are operations that are applied to the same object, where at least one of the operations is a right. So as has come up before, if we have two concurrent reads of the same data, they both see the same data there, they both read it, there's no issue having concurrent reads. But if we have a write and another write, or a write and other reads, then there's the potential for them to interfere with each other. So that's what we'll call conflicting operations. And there's kind of three specific anomalies that we're going to want to avoid when it comes to conflicting operations. We have our read-write conflicts, which are also called unrepeatable reads. We read some value that if we read the same data again later in the transaction, we're going to get something different. And so if we have our transaction 1, it reads A, and then later on it reads A again, and in the meantime, transaction 2 has read A and then written A. Then maybe our transaction 1 reads 10, transaction 2, it reads 10, but then it writes 19. It updates A to be 19, and so then when we read A again in transaction 1, we get 19. So this is transaction 1 is not getting the picture of isolation if it reads A without making any changes to it and gets different values. In our write-read conflicts, these are sometimes called dirty reads, and it just means we're reading uncommitted data. So if we have transaction 1 read A and then write A, transaction 2, it reads A, it writes A, but then and then it commits again, and there's a begin here. And so if our transaction 1 reads A, it sees 10, it updates A to 12, and then transaction 2 reads A, finds 12, adds 2 again, updates it to 14, and then transaction 1 aborts. Well, this is a problem because transaction 2 already committed, told the world that A is now 14, but in doing so, it leaked information about what this aborted transaction T1 did. The fact that it updated A to 12, and that influenced what T2 did. If we want our transactions to have this isolation property, it shouldn't be the case that changes made in an aborted transaction can be committed to our database by virtue of being read by some other one. So that's this write-read conflicts are dirty reads, and finally we have our write-write, which is going to be when we're overwriting committed data. So in our final example, we have T1 writes A, T2 begin, it writes A, it writes B, it commits, and then later on T1 writes B and commits. And so let's say that T1 wrote 10 to A, and then T2 wrote 21 to A, and it wrote Aaron to B, and then T1 wrote Howie to B. So here, when both of these have committed, we have the value of A from T2 and the value of B from T1. And so our update has, our database does not reflect the effects of our transactions as if they had run in a sequential order. We have what's sometimes called a torn update, where we have an update to A and B that's the effects of which are kind of split across two transactions because they were allowed to interleave in this problematic way. And so what we will want to do in order to avoid these potential conflicts, these potential problems, is we will want to have what are called conflict serializable schedules. And this idea of conflict serializable is going to tell us how to check, how to tell whether a schedule is correct or not. This idea is not going to tell us how to generate a correct schedule. How we will generate correct schedules is coming in our next two videos on concurrency control. But for now, we just want to establish how do we know, given a schedule, whether it is correct, whether it is conflict serializable. So for a schedule to be conflict serializable, it needs to be conflict equivalent to a serial schedule. And what conflict equivalent means is the two schedules involve the same operations, as part of the same transactions, and every pair of conflicting operations, and remember in operation, two operations conflict if they're from the same transaction applied to the same, from the same transactions applied to the same object, and one of them is a write. So every pair of conflicting operations appear in the same order between our two schedules. Those schedules are said to be conflict equivalent. And so what we want is for our conflict serializable schedule is its conflict equivalent to some serial schedule. We can actually use a graph to do this, and we can build up a dependency graph. I believe the textbook calls this a precedence graph. And how this will work is we'll have a graph of our transactions. So we have T1, we have T2, and throw in a T3, and we'll put an arrow from one transaction to another. So this will be a directed graph. We'll put an arrow from one transaction to another. And we'll add an edge if we have a conflicting operation in T3 and T2, and it's the case that it happens in T3 first. So this means that we have this conflicting operation that first occurs. Say there's a read of A in T3 and a write of A in T2. Then we would add this edge to our dependency graph in order to show this. And so if we have a kind of 3 transaction schedule like so, where we begin T1, read A, write A. Actually, we'll just do a 2 transaction one to start, and then T2 reads and writes B, and then T1 reads and writes B. In this case, we would not have our T3 in here, and we would say, all right, so there's a conflicting operations, say a write to A in T1 and a read to A in T2, and so we draw an edge from T1 to T2. There's a conflicting operation on A, and it happens first in T1. Then we can look at B. There's a write to B and then a read to B first in T2 and then T1. So we add an edge back here, and the reason that this graph is helpful is that the presence of a cycle, the presence of a loop in our directed graph means that our schedule is not conflict serializable. So in fact, our schedule is conflict serializable if and only if its dependency graph has no cycles. So this bad schedule that we saw an example of before would produce a dependency graph with a cycle, and therefore we could detect that this schedule is not conflict serializable. To see how this would work in another example, we'll go to our third 3 transactions, and we'll have T1 read and write A, then we'll have T3 read and write A, then T2, read and write B, add in some commits, and then finally T1 reads and writes B, and then commits. And so if we build up the dependency graph for this, we see that T1 and T3 have these conflicting operations on A, and T1 happens first, so we'll draw an arrow from T1 to T3. We then see that T1 and T2 have conflicting operations on B, where T2 happens first, so we'll draw an arrow there. And that is all of our conflicting operations, and our dependency graph does not have a cycle, meaning that this schedule is conflict serializable. We could, it is equivalent to a serial schedule, and in particular, it's equivalent to the topological sort of our acyclic graph, and so that so it's equivalent to if we did T2 and then T1 and then T3, we would have the effect of this schedule is the same as the effect of the sequential schedule, the serial schedule, where we do 2, then 1, then 3 among these transactions. All right, so the last acid property, durability. This is where we're kind of writing to disk to ensure that our data is persistent, and we'll talk a lot more about how we enforce that in different scenarios when we get to logging and crash recovery in our last week of the course. All right, so with that, that will do it for our concurrency control theory, and the next 2 videos will be about how we actually generate these correct schedules now that we kind of have the definitions for what a correct schedule is. So with that, I look forward to your questions. Ooh, huh? What is there? It's using my own words against me. This is outrageous. This is ridiculous. I demand it. I never.